Hi there, and thanks for joining me today. Today I'm going to talk about analog mapping, more specifically analog mapping for electrical throttle and braking applications. As you can see on the slide in front of you, we've got various types of sensor feedback devices which can be used to interface to a motor controller to provide commands to set speed, torque, braking torque, etc. for motors. Fundamentally, we have two real types of devices that you'll see in industry and such, and that's resistive potentiometer-based devices and Hall-based devices. Both provide adequate feedback for motor controllers, but the resistive elements are a little bit more finicky in that they take more to seal up. They have a little bit higher wear mechanisms, and they're just in generally not a very robust or as robust device compared to the Hall-based systems. Places where you might see some of these devices would be ranging from e-bike applications with the thumb and twist throttles to electric tractor applications with the brake pedals and accelerators to forklift applications with the gimbal throttle mechanisms. They're found in quite a few different applications. So now that we know where these devices are used, let's talk a little bit about some definitions. So when a feedback sensor is actually installed and powered up for the first time, it will have what we term an offset value, which is its resting output value. When the sensor is actually actuated and forced to go through its full motion of travel, the resulting difference between its final and offset value is termed the range of the sensor. Since the sensor itself is mechanically fastened to wherever location is being used and typically has a linkage of some sort actually connected to it, the repeatability of the offset and range values can vary dramatically from operation to operation and day to day. With this in mind, the concept of a deadband is introduced. So a deadband provides a location within the sensor reading that is ignored more or less for any changes in the sensor. So it's a fixed output value. So placing a deadband around the offset and around the maximum output of the sensor allows us to firm up a location at which we decide that the range, the usable range, will be made. This means that we can define a zero starting point for the sensor and an end point for the sensor, which is consistent for every operation. The last little item I want to mention is about linearization of the sensor feedback signal. For every implementation of a sensor, the resulting output may or may not have a linear relationship with the motion of travel. If the signal doesn't have the linear relationship that you're expecting, then further modification of this signal to provide different feel of control will be difficult. So we tend to provide a lookup table or equation which will straighten out the response for the motion of travel. Okay, so now we kind of define some of the concepts around deadbands, offsets, and sensor ranges, etc. We can talk a little bit about the actual analog mapping in general. So a nice little comment to say is that people really don't feel linear. And a good example is the audio world where you've got logarithmic volume control. Small volume changes can be detected very easily by the human ear, but as the sound pressure gets higher, those differences become harder to distinguish. Now, if you take the volume example and apply it to motor control, It's very similar feel in that you can detect small changes in torque on a motor at low speed because you can feel the jerkiness of the response. But as your speed increases, that small changes in torque are not as noticeable. The same with sound. At low sound volumes, small changes in volume are very noticeable, but as the sound level gets higher, those small changes then become less noticeable. It's for this reason that we don't use a linear response for controlling motors in torque mode. So here we see like three curves, one linear, one non-linear, and one exponential. So this kind of represents the output from a sensor being non-linear, then us linearizing it to allow us to then apply a new mapping to make it into more of an exponential type curve. So if we were to consider torque control of a motor and you looked at these three curves, the linear curve would have a fairly sharp response at low torque values, and as such you would see a lot of jerking of the motor. With the exponential mapping, this flattens out the response below 50% actuation and makes it far easier to control the torque at low values. But as you go beyond the 50% point, the torque climbs very quickly, and this becomes a lot more natural response. Okay, so let's go take a look at how we would create a new mapping for a sensor input. Now the sensors themselves are going to be mechanically attached to something with a linkage that prevents it probably from achieving its maximum design output and its minimum design output. So you're going to have a resting voltage, which we refer to as the voltage offset, when the device hasn't actually been moved from its resting spot. Between the limits of what it can do, so its minimum and maximum values, you can assign the deadbands to make sure that you can have a consistent starting point and end point throughout the travel of the sensor. Placement of the deadbands is pretty critical in ensuring that you can get maximum usable range out of your sensor. The beginning deadband will typically extend past the voltage offset point by X% and go from that point down to the zero voltage. The upper deadband will typically cover from X% below the maximum sensor output and go all the way up to what the maximum achievable output would be. Now that we have deadbands on the upper and lower limits of the sensor output, the usable range is now well defined. In addition to having a well-defined usable range, any drift in the voltage offset of the sensor or the change in the endpoint of the output of the sensor will not actually impact that usable range. The next step in making this mapping work for us is to take the usable range that we've created between the two deadbands and now actually remove the offset to bring it to a zero starting point and scale it so that it will range between 0 and 100%. If the sensor output is not linear, then a mapping or equation may be used to make it a straight line relationship. Another great feature to include if you're considering doing this process is fault detection. Now, fault detection looks at the extremes of the sensor outputs and drives a fault if you enter that region of operation. An example where fault detection is really great to have is in the case of vehicle operation. If your sensor fails in a high state where it's putting out maximum output, and that's interpreted as maximum throttle response or maximum torque response, then you can have a runaway condition. If your fault detection is looking for a signal that is now outside your deadband or above what your maximum sensor output could possibly produce, then you have a chance to shut down gracefully. I hope that this video has been useful and that it gives you some ideas on how you may approach doing analog mapping for sensor outputs. And if you find it useful, please give it a thumbs up. Thanks.